Hi everyone, this is VK. Welcome to Smid World. Here I am with another video. Combustion techniques and cold flame for cement kiln. Principles of combustion. Always to be remembered, if coal is mixed, it is burned. If the flame is wrong, everything goes wrong. Whatever you may do with chemistry or higher heat input through calciner or the burning zone needs heat and it can be only obtained from well-shaped radiant flame that is short, snappy and convergent flame. Kinetics of coal combustion in kilns. The coal combustion phenomena in a cement rotary kiln takes place in four stages. For normal coal, first one is heating. Heating of coal particles takes place by conduction and convection till ignition takes place in reach. Ignition temperature of bituminous coal 300 degrees centigrade, lignite 250 degrees centigrade, anthracite 400 degree, petcoke 800 degree. Devolatilization. Devolatilization process starts after the coal particles attain a temperature of 350 to 400 degrees centigrade. At this temperature, the coal bond structure breaks up to yield carbon monoxide, hydrogen and hydrocarbons. Volatile burning. The volatiles that are formed burn in gas phase and the rate of burning depend upon two factors. The rate at which the volatile mix with the air after being emitted from the coal particles and the rate of chemical reaction. Fourth point, residual char burning. The residual char is the solid carbon left after complete devolatilization. As the reaction progresses, the residual char starts to take up to 70 to 80% of total burning time. You can see here reaction, heat and oxygen turns to volatile matter evolution and burning, then char gasification and combustion, then it is split into CO2, H2O, NOx, SOx, etc. Balance is char. Coal combustion process. Original coal to drying, drying to devolatilization, then char burning. Main process in coal combustion, coal particles 30 to 70 microns goes to devolatilization, then volatiles and char, volatiles to homogeneous combustion HCO2, H2O and heterogeneous combustion. Stages of coal combustion. The coal particle drying and then heating up to pyrolysis reaction temperature. Pyrolysis of the coal particle to produce non-condensable volatiles or condensable volatiles and carbonaceous char. Oxidation of the combustible volatiles and finally char oxidation. Reburning. Excess air. Devolatilization. Volatiles and char. Homogeneous combustion. Heterogeneous combustion. Staged combustion, fuel rich. Combustion time as a function of particle diameter. The combustion time T is equal to KD power of 1.5, whereas D is equal to diameter of coal particle, K is equal to constant characteristics of coal quality, low for bituminous coal, high for pet coke. That is why we remain high residue for bitumen coal and low residue for pet coke. The faster the combustion or gases are removed and replaced by fresh air, the faster the coal particle burn to fulfill is a precondition. The high relative velocity between combustion air and coal particle is required. This needs a high flame momentum with high primary air velocity and low percentage of primary air. Relationship between coal types and composition and grinding fineness. Combustion time for a particular coal particle. The physical process influencing pulverized coal combustion. The first point, turbulent or a swelling flow of air and coal. Second, turbulent or convective or molecular diffusion of gaseous reacts and products. Convective heat transfer through gas and between the gas and coal particle. Radiative heat transfer between gas and the coal particles and between coal air mixture and the furnace walls. Coal combustion chars. When coal is combusted in air, it burns into two-step process. The first step, gases are driven out of the coal structure, leaving behind carbon chars that burns in the second step. These chars play a critical role in combustion in that they must burn up to in the reaction zone of the furnace or be carried out of furnace as unburned carbon in fly ash. This unburned carbon represents an inefficiency as well as uh, economic losses because the energy in the unburned carbon is not being used. Excess unburned carbon also destroys the ability of the fly ash to be used as cement in a variant of applications. In modern combustion system, coal is usually ground into a fine powder, 74 micrometers, that features may single metal particles. This is significant in the various materials tend to have different reactivities and therefore bind at different rates because the different materials grouped from charts with different morphologies. It is possible to analyze coal combustion charts to gain information about the nature and reactivity of coals being combusted. The vitrinite mercurials from charts that take from form of hollow spheres, centispheres, semi-fusionite minerals from centispheres with a lacy or honeycomb structure and fusionite mineral char come through the combustion process unfused. The coal combustion char classification. Unisphere means fused or partially fused hollow spherical or angular char with walls less than 10 micrometers and porosity greater than 85%. Acisphere fused to partially fused hollow spherical or angular char with walls thicker than 10 micrometers and porosity greater than 75%. Tunnel network partially fused thin wall char with internal network structure and porosity greater than 75%. Mesosphere partly fused thin wall char with internal network structure and porosity 40 to 60%. Inertoid unfused particles with a rectangular to irregular shape and low porosity of 5 to 40%. Solid unfused particle with a rectangular to irregular shape and no porosity. Fissionoid unfused particle resembling fissionite with original plate cell structure. Mixed porous mixed particles showing both fused and unfused sections with fused porous section dominant. Mixed dense mixed particles showing both fused and unfused sections with unfused porous sections dominant. Skeletal unfusing angular but highly burnt or charred, still resembling finite mineraloid. Char with over 50% of mineral matter. Smaller, this balloon like a space and thinner its wall. Faster the combustion, it is very difficult to form such space, cyanosphere, from the pet coke because of low volatile presence. It needs very high energy and longer. Retention time in ignition zone. Description: the object in the center of the field is typically tunisphere. It is characterized by its spheroidal shape and open center and thin walls. The charm forms such as hollow spheres, also called cyanospheres, before mixed with oxygen to form gases of various oxides, easily pressed in microparticles of carbon. Combustion of char. Once the ignition has occurred, the critical reaction as far as the good combustion kiln is concerned are, you can see here formula. The effect of coal properties on combustion. Moisture content. A moisture content of 1 to 1.5% in the pulverized coal promotes combustion. In the presence of hydrogens, the formation CO and CO2 takes place by chain reaction. On the other hand, a higher moisture content increases the thermal inertia of reactant species, shifts the flame and reduces the flame temperature. The volatile rich coal has a high porosity, offering a large space area for combustion, hence requiring a lower ignition temperature than volatile less coal. Example: anthracite, pet coke, etc. Thus, the coal-rich volatile matter greater than 30% decomposes with a higher rate and promotes faster combustion. Volatile rich coal from small ionospheres with thin walls and decompose faster. Ash. Ash is an inner component of coal and an increase in quantity leads to increase in heating time due to added thermal inertia. Most of the combustible particles of coal will be covered by ash and hence less surface is available for oxygen diffusion. This increases the burning time and the residual char causing an increase in flame length. So overall, there is delay in combustion, elongates the flame. If there is a cloud of clinker dust, what will happen? This dust will absorb the radiated heat from flame, reduce the heat flow to the refractory, and get reheated with more stickiness. Hence, optimized cooler airflow with good clinker bed, overall cooler efficiency operation will enhance the combustion efficiency. Effect of coal moisture content on degree of combustion versus distance from the burner. Effect of coal moisture on flame temperature versus distance from burner. Effect of volatile content on degree of combustion versus distance from burner. Effect of secondary air velocity on flame temperature versus distance from the burner. Effect of oxygen level on exit gas heat loss. Simulated oxygen content for an ideal flame. Flame. Cement kiln flame types. Straight flame, essentially external recirculation. Type 1 flame, weak internal recirculation, external recirculation. Type 2 flame, strong internal recirculation and external recirculation. Recirculation zone, baffles, shorter flame, dual recirculation zone. The straight flame of a single channel burner. The straight flame is stabilized single pipe burner by the strength of the external recirculation flow established by the shear force between the primary and secondary air streams. Multi-channel burner. For multi-annual burners, enhancing the internal recirculation flow patterns can increase the flame stability. This can be accomplished by reducing the momentum of the inner zones while increasing the momentum of the outer air zones, or by mounting a bluff body flame stabilizer in front of the primary stream. Heat transfers from coal dust flames. Fuel gases or flame gases respectively pass their heat to the environment mainly by radiation and only to a small degree by conduction and convection. Normally 13% of the kiln volume is usually filled. Therefore, major portion of the heat is transferred to kiln refractory lining with the kiln feed receiving a relatively small portion of the total heat volume. Many try to keep the flame close to change but has negative influences as coal may get trapped and cause reducing conditions in the charge which causes reduction of Fe2O3 and also volatile recycling of alkalis and sulfur. If it is close to charge which is 13 to 18%, the heat radiated to refractory weakened and cause poor heat exchange. The heat is carried always by the flue gases only to result in high back-end temperature. If the kiln has stable and optimum coating, then we get the best heat exchange as it acts as the best heat reservoir. Burner positioning. We do positioning of the burner of centering the flame. The positions 1, 2, 3, 4 and 7 are close to the refractory and they are away from the charge. The position of 9 and 8 are close to the charge. Only 5 is close to the charge and refractory and this is best as a flame in this gives the best thermal distribution to effective burning. The position 8 and 9 is very close to charge. If the coal is trapped, it has serious negative impact. Position 147 is very close to refractory and it can burn the refractory. Flame positioning towards the charge. There is an illusion if the bunker is kept just above the charge or impedes the charge burning is better but is on the other way. In heat exchanges process, 85% of the heat is radiated to refractory and 15% to the charge. If the flame is kept above the flame, beyond the plum, it is invisible. If we are not careful, the char takes more time to burn out and hence it is highly possible the char gets trapped. From local reducing condition, reduce the hematite, spoils the liquid and increase the recycle of sulfurous cycles. The rules of radiation of solids cannot be applied by the radiation of flames. Monatomic and diatomic gases like N2 and O2 are in the range of infrared, entirely transparent, and their radiation equals to zero. Therefore, the presence of these gases is only ballast. On the other hand, gases with a higher number of atoms such as CO2 and SO2 develop a considerable thermal radiation due to their absorption bands in the higher range. CO2 radiates more than the others. The radiation active constituents of the pulverized coal flame are CO2 content of the flame gases, H2O content of the flame gases, C the content of suspended dust in the flame gases. The following requirements result in promoting the heat transfer by the gases in the clinkerization zone. An increase in the flame temperature, an increase in the concentration of CO2, an increase in the kiln diameter to have 13% degree of filling. Thick coating increases the degree of filling, reduces the effective diameter of 300 mm thickness is considered as ideal to improve refractory life as well as the heat exchange process. Multi-channel burner, traditional burner. Function of burner or requisites of a good flame. First point, the burner must be able to burn fuel with a low excess air and with a minimum generation of carbon monoxide, nitrogen oxides and volatile recycling like SO2, etc. Burner must be able to produce a short, narrow and strongly radiant flame which is required for good heat transfer from flame to material in the centering zone of the kiln. The flame formation must be conducive to the formation of a dense stable coating on the refractory in the burning zone of a kiln as well as a nodular clinker with a low dust content and correctly developed clinker minerals. The burner must use as little primary air possible since primary air is basically false air. Flame momentum. The burner in kiln functions as an injector, the purpose of which is to draw the secondary air coming from the cooler into flame in order to burn the fuel as near the center of kiln as possible. This explains why momentum of the burner is the deciding factor of the flame formation. Multi-channel burner makes a faster entrainment of secondary air than single-channel burner. Higher the momentum, better the entrainment of secondary air and faster the combustion of air. The momentum or impulse equal to percentage of primary air. Here you can see the formula. Secondary air velocity 5 to 6 meters per second. Ignition this depends upon the rate of mixing of secondary air and coal particles, size of the fuel particles and volatile content and the injection velocity. And the secondary air taking area. This depends on the pressure differences between the secondary air region and the primary air region. Higher the pressure differentiates higher inner circulation and outside circulation recirculated combustion gas area. If the jet has good momentum, it will pull back the fuel gases, causing the external recirculation. This is an indication of secondary air entrainment into the primary air jet. Multi-channel burners do this job efficiently. This reduces the NOx formation. You can see in clear picture axial outer stream, swill core plus transport air and swill inner stream. Ignition area, secondary air taking area and recirculated combustion gas area. Restrict to coaxial flames. Types O flames, no secondary air spill, no internal circulation zone. And represents corner fired boilers and cement kilns. Well defined aerodynamically, flame standoff distance has been identified as key parameters for NOx emissions in cement kilns. Different flames. Flame at the center. Normal flame, flame downward, flame with low secondary air temperature, distort nozzle, Flame upward direction. Flame poor good distorted nozzle. Normal snappy flame forms dense and stable coating, indication of first dam. Long lazy flame with unstable coating. Secondary air velocity versus flame length. Secondary air velocity influences flame length and shape. Higher the secondary air velocity, longer is the flame. Here we have to increase the flame momentum by increasing the primary air velocity at the tip. Higher the secondary air velocity, lower the hotter pressure region, hence we have to increase the pressure drop at the tip to pull back more secondary air towards the coating at the tip, called shark teeth. Increase the secondary air velocity and so increase the flame length. Flame troubleshooting. Pulsating flame with CO peaks at the kiln inlet. Fluctuations in coal flow. Check the flow parameters. Clean the bin as there many coat as there may be coating formation. Check the liners in the cone. Bin. Dusting pressure should be maintained. Coal flow discharge chute can have coating formation and ununiform gap between a screw flight and a casing. Firing pump discharge flap counterweights needs adjustment. Redusting for coal feeders device to be optimum. If FK pump seal is leaking, transport air can go inside the pump screw and fluidize the coal and, and change its bulk density, and hence the flow pump is a volumetric transport device. Insufficient secondary air temperature and flow variation. Optimize the clinker bed and cooler and cooling air to recuperate. Optimize the clinker bed and cooler and cooling air to recuperate more heat. Reduce the variations in the undergrade pressure as well as hood pressure pulsation. If the shock blasters are 3 air, adjust the time interval to avoid pressurization of hood. Insufficient transport air velocity or coal injection velocity. Check the material and air ratio. It is 4 kg coal per cubic meter air to 6 kgs. The velocity is 25 to 30 meters per second. If it is not so, modify the transport pipe inner dia or increase the transport air volume. Too long transport air pipe. The maximum length is 250 meters. Avoid sharp bends, and these bends will cause pressure variations. During layout itself it should be considered. Check the coarseness of coal. To coarse coal can settle in the pipeline. Flame characterized by a long black core. Increased CO value at the kiln inlet. First point, too high coal injection velocity. It is normally 25 to 30 meters per second. Increase the coal pipe annular space at the tip to have 25 to 30 meters per second tip velocity. Plants run with lesser than 25 meters per second also. Insufficient mixing of coal and secondary air. Low secondary air temperature. Arrest false air increase through nose ring by cooling fan or false outlet sealing. Third point, coarse coal. Check the separator, increase the fineness. Flame burning at the burner tip or sometimes coal drops. Too low coal injection velocity. This may be due to rotor gap to blow has increased or the blower filter got choked. If the coal pipe got punctured inside the burner, coal will mix with the primary airflow and damage further. Check for wear of coal injection pipe tip or monitor filter DP and rotor gap. Excessive spill air. Optimize the spill air. Flame burning. First one. Partial pipe clogging due to foreign matters existing in coal channel. Remove the foreign matter. When we do the casting, ensure that uh, wet castable mix should not drop into the burner. Close the burner by a plate vessel casting. Worn out centering element for coal channel or air channel. Unequal spacing of airflow annular space. Alignment of burner channels so that annular spacing is equal for coal flow pipe as well for primary airflow. Coal pipe got punctured inside the burner and coal flows into primary airflow channels. Change the burner along with the coal injection pipe. As per pilot, a burner needs to changes when coal quality changes. You can see here three columns: coal property, effect, and burner adjustment. Characteristics of flames with and without recirculation. Fuel or air mixing, flame with recirculation, flame without recirculation. Burner spill number, spill coefficient, airflow dynamics, axial index, tangential index, turbulence index, dispersion index. Thank you for your kind information. If you have any doubts, do let me know and write in comment section so that we can do videos on them. Thank you.